In this short video, we're going to look at how to tackle word problems. And we're going to do it specifically for a conversion problem. And this is going to be useful both in chemistry and in physics because it's going to help us tackle what information is provided, what is it we need, and give us a little bit of a strategy as to how we're going to utilize or how we're going to use the information and utilize our toolkits that we have gotten through either our chemistry class or our physics class. I want to comment that I'm building this primarily for my general physics class, but it is applicable to general chemistry, and I am going to be using our textbook Serway and Jewett from college physics to give you a generalized problem-solving method, and I have referenced that in these slides. So we do have permission to use the information from those textbooks, and I am actually referencing them as well. Also, you'll notice that I'm referencing an image here, and I have used AI to generate it using Adobe Firefly, and I have given you the prompt. So let's take the problem. Let's read the problem. So the first step in any problem solving or in anything that we're doing is that we want to read what the problem gives us. Now, we're notorious in physics and chemistry for giving you more information than you need. And a lot of that is because you're looking at how that information is going to be used for multiple problems. So we'll use the same data over and over again. Sometimes we're just being mean, cruel, and wicked, and we're using that data and we're just giving you extraneous information, and it's up to you to solve and figure that out. So let's look at this problem. A traveler in 1860 would travel by stagecoach from Muddy Gap to Independence Rock. And I've actually made this trip. It's in Wyoming, and you go on an intersection, and it takes you about an hour to get there. It takes maybe a little longer depending on what wildlife that you see on the way. And it's in Wyoming, but it's approximately 63 miles between Muddy Gap and Independence Rock. The literature for the ride indicates that they will be traveling at a rate of 33.6 furlongs per hour. The brochure also indicates that it will take 3 days with 2 overnight stops. Today, the traveler can make that trip in about an hour, and I've done it, traveling at a speed of about 65 miles per hour. And what we want to know is, because that is an old-timey or a historical unit of measure, although we still use that unit of measure furlongs per hour or furlongs per minute in horse racing. If we're typically looking at it, if you look at the Kentucky Derby or something else, that furlong is still utilized in horse racing. So we're going to look at that older unit of measurement that we don't typically use, and we're going to convert it into something that we have a little bit more familiarity with: miles per hour and meters per second. So we want to translate that 33.6 furlongs per hour into our miles per hour. So let's look at the approach to the problem here. And I'm going to move myself so that we can talk through this. So we still have the same problem. So this is a typical word problem methodology that we're looking at. What is it we want to know? Well, in this case, we'll look at exactly what it is we want to know, and what do we know? What is provided in the problem? What information is missing? And then as we start to do more complicated problems or start to working with additional problems, we want to know what tools or equations or methodologies or graphs that can help us solve the problem. So basically, when we get a word problem, think of it as a puzzle. What do we have? What pieces do we have? Do we have all the pieces that we want or we need? And where else can we get that information? Because in a lot of times, both in chemistry and physics, we have extraneous resources. In chemistry, that could be the periodic table. In physics, those could be fundamental constants of the universe. But in this problem, there's a lot of information that we can get that may not be given to us in the problem, and that's our list of conversion factors. So we're actually going to look at that. So let's take the next step of the problem here. So since we already looked at our issue of what do we know, and what do we want to know, and what information do we have, let's look at what do we know. We know that the traveler is going 33.6 furlongs per hour. We also know there's a total distance of 63 miles. And again, because this is chemistry or physics, we know that sometimes we may get a part B or a part C or a part D of the question. But in this case, we're just going to be looking at that 33.6 furlongs per hour. Well, what is it we want to know? We want to know the speed in miles per hour, and we want to know the speed in meters per second. And the information that's missing are conversion factors. Now, since we're just getting started in chemistry and physics, we don't necessarily have a big toolkit other than what we come into the class with. And we have been doing conversions since we were little kids. For example, if I'm in the kitchen and I want to double a recipe, or I want to half a recipe, I know that 1 cup can be 4 quarter cups, or 1 cup can be 3 third cups, or 2 cups can be a pint. All of those are conversion factors, and a lot of times we're doing those conversion factors in our head. What happens to us when we get to a chemistry class or a physics class, all of that seems to go out the window, because somewhere along the line we were told that chemistry and physics is hard. Well, it's just using information that you already know in a slightly different way. So we're looking at that conversions, and we've done those conversions over and over again, and we've dealt with that over and over again. For example, if you know that your car is getting 40 miles to the gallon and your tank is currently on a quarter of a tank, which in my car would only leave you about 4 gallons because I have a small car, I know that I might be able to stretch it to the next exit. And that's something we do in our head because it's familiar to us. When we're using problems like this in word problems, we're not necessarily looking at familiar information. So we want to start making that a little bit more familiar. So let's take our next step. So here we go. That's the information that we already have, and I can put myself over that. So we need those conversion factors. So I've given us a table of conversion factor. We know that 1 furlong is 0.125 miles. 1 mile is 1609 meters. 1 hour is 60 minutes, and 1 minute is 60 seconds. These are equivalent statements. If I do 1 furlong divided by 0.125 miles, that's just a 1. And I can multiply by 1 all day long. But I've got to use those units, and this is where we talk about unit or dimensional analysis. Numbers have units, and in order to work these problems, we need to watch those units. And we need to be able to utilize those units, and doing that unit analysis is really going to save us. And that's going to give us, did we set up the problem correctly? And as we work through and get more complex problems, we're going to see that over and over again. So these are equivalent statements. So let's look at the next one. So let's take our next approach. So what is it we really want to do? We want to move from furlongs per hour to miles per hour. And once we get that information, it's a lot easier to move from miles per hour to meters per second, because we'll do that one a lot. We do that one a lot. If you go to Canada, you go to Europe, where they're working in kilometers per hour, you're going to make that conversion between miles per hour to kilometers per hour or meters per second. But one of the things for my physics students, we want to look at meters per second because we don't usually work in meters per second. And when I talk to folks, I give them, when we look at numbers, like for example, 365, if I just give you 365, you know that 365 is just a number. It could be 365 apples, it could be 365 pallets, it could be all kinds of different things. Typically, we're immediately going to think of 365 days per year. But when I give you the number 27, that doesn't mean anything to us, and that's not a typical conversion factor that we have in our head. And in physics, 27 meters per second is really, really close to 60 miles per hour. And that's going to give us that last little bit of information that we're going to need to verify, do we have the right answer? Because when we look at the overall generalized problem-solving strategy, you'll want to be able to look at what that means and give yourself a way to validate your answer. So let's kind of go on to the next. So we've got that part. So now let's do the actual calculation. So I'm going to go ahead and cover our units here, and so that you can still, no, I guess I can move myself down here so we can still see the units. There we go. So we're going to go from furlongs per hour to miles per hour. So let's write it out so that we can kind of start to see that. I had something pop up on my screen. We're going to write it out, and we're going to see that. So here I have it. I've got 33.6 furlongs per hour. That's coming right from our problem here. And we want to get to miles per hour. This is where my unit analysis comes in with my equivalent statement. So I've got 33.6 furlongs per hour. And here's my equivalent, 0.125 miles. That is 1 furlong. Now, when I do this, this 1 has infinite significant figures. So that's not going to control my significant figures calculation for those of us that are in chemistry and we want to keep track of our significant figures. We want to look at that. So this equivalent statement, again, because it really is 1 furlong is 1/8 of a mile, we really have infinite number of significant figures. So in this case, my equivalent statement isn't going to control my significant figures. So I've got 33.6 furlongs per hour. And just to refresh our memories, that's 3 significant figures. And now I'm going to multiply by 0.125, and I'm going to divide by 1. Because sometimes my equivalent statements could be 3 of this is equal to 2 of something else. So when we get down into chemistry, we will see that a lot as we are doing our balancing equations, as we're working with those pieces. So those equivalent statements may look a little different. So but in our conversion problems, it's usually pretty straightforward. I usually have a 1, but this right here is just 1. So I can multiply this number by 1 without affecting anything. Now I have furlongs in the numerator and I have furlongs in the denominator. So my furlongs are going to cancel out and I'm going to be left with miles per hour. So here I am, miles per hour. So I do this, I plug this into my calculator, and my calculator is actually going to give me 4.2. 4.2 is only 2 significant figures. And if I'm keeping track of my significant figures, I want to make sure that I've got 3 significant figures. This is not controlling my significant figures because this case, those are infinite. And so there it is. This is what's going to control my significant figures. So I'm multiplying by 3 significant figures. So my answer better be in 3 significant figures. So now we can take our answer there and let's go ahead and do the next one and convert to our meters per second. So I've got my 4.20 miles per hour, 3 significant figures. That 0 is significant. Now in this case, 1609 is not an exact number. And if you go look up the conversion factor, you'll find out that it's 16.9 or 1609 point something 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 something. But again, this has more significant figures than what we're starting with, so we don't have to make any adjustments here. We're going to be in an answer with 3 significant figures. The case of 1 hour is 60 minutes and 1 hour is 60 seconds. Those have infinite significant figures, so we don't have to worry about those causing us any change in our significant figures. So now I'm going to do my 4.2 times my 16.09. I'm going to divide by 60. I'm going to divide by 60 again, and we're going to be traveling in the stagecoach at 1.88 meters per second. So we will use this Newton analysis. So let's look at it again. I've got miles in the numerator, miles in the denominator, and I'm left with meters, and meters is what I want. I've got hours in the denominator. I'd have hours in the numerator so that when I do this calculation, I'll be in meters per minute. And then I've got to get rid of my minutes. So my minutes in the numerator, minutes in the denominator, they'll cancel out, and I'll end up with 60 seconds, and I'll end up with meters per second. So my unit analysis, if I keep my numbers with their units, it's going to tell me if I put it in wrong. If I did this flipped over, it's still 1, but I don't get units that make any sense. So I want to look at those units. So now let's take a little quick second here and let's look at the problem solving strategy that's taken from the college physics text. That a general problem solving strategy when we're dealing with physics problems or chemistry problems, there's only a couple of steps different here, is no matter what you do, you want to read the problem. You want to read the problem. You may want to read it a couple of times. You may want to jot down what you think you know. And a lot of things right now, because we're working on the computer, a lot of times we're trying to do it in our head. Please use scrap paper. Please use nice paper on your, go ahead and use the paper. Write things out. You may want to write out the whole problem. It may help you figure out what you need to do. But you want to read the problem, so you want to understand what you're starting with and where you're headed. You want to draw the diagram. For physics, drawing that diagram is essential. Sometimes in chemistry, it's not as critical, but you may want to do a diagram of how I'm doing this reaction. You may want to do a process flow, but there's usually something in there that you want to look at and make sure that you have it. You want to label your physical quantities. If I'm doing it in physics, I may have gone back to my original picture and drew my little stagecoach, drew a straight line, drew the mountain, wrote the information out over the line. So you want to label your picture to make sure you have everything in there. Then you want to identify the knowns and unknowns. Again, that's that same simple word problem strategy that we've used since we were in elementary school. We read the problem, we look at what we know, we look at what we don't know, and we see if we have all the information that we need. Then write down the equations that you might use. In our conversion example, we didn't necessarily have an equation that we would use. We're going to have to build that equation by using those equivalent statements. And those equivalent statements came from our conversion tables, but we got that together so that we can make it work. We're going to then go and we're going to solve our problem. We're going to substitute the known values for the problem. This will, in physics, you may want to do it algebraically first. So you want to look at it there, and then you want to check your answer. Does your answer make sense? Now, if we go back and we look at our original problem, so let's go back one and let's look at our original problem. We were traveling at 33.6 furlongs per hour, and it said it's going to take us 3 days. And the reason we're going to do that is because we want to save the horses. And we're not going to stress the horses too much, so we're traveling at roughly 4.2 miles per hour. So we're not going very fast. So that to have something that's 1.88 meters per second is not necessarily a number that's going to be outrageous. So this is going to look pretty good. We also want to check our significant figures. We want to, you may want to plug it into your calculator a couple more times to make sure that everything is going well. But that is our approach. So I'm going to leave you with a general problem solving strategy. Hopefully this helped you with some conversions. I actually looked at equivalent statements, gave you a couple of methodologies on how to approach word problems, and hopefully that will help.